In the previous video, I wanted you to have a good understanding of how a double summation works, but now we'll just go ahead and execute the actual task of finding one convolution. Let's just suppose, to keep things simple and to not take up many pages of space, that y is a 4x4 image. So we have a tiny 4x4 image, and it has these pixel values. Again, remember we're working with grayscale, so this would be black and white. And the values of k in our kernel, let's just say, without giving this any justification why for now, just so we can practice the computation, let's say this is our kernel matrix. And we want to find the convolution of between y and k at position 2, 2. So because we are working with our indices as 0, 1, 2, 3, 0, 1, 2, 3, then remember this is -1, 0, 1, -1, 0, 1. The position of 2, 2 is actually going to be this 8. Okay, this 8 is position 2, 2. Okay, so what we're focusing on then is the 3x3 that has position 2, 2 in its center. Now remember the way that this works, if we back up a little bit, the way we multiply the 9 values is in the kernel, we start at the top left, and we multiply that by the 3x3 subset of our image at the bottom right corner. And then we move over to the next column within the same row of the kernel and multiply that by the -1 column in the y matrix. So it's going to look like this. So we are going to start off with this value here, 5 times -1. Okay, so y convolved, sometimes you can say convolved with k at 2, 2, will first of all involve the y value times the kernel value, 5 times -1, plus, okay, now we need to take the next kernel value, -1 times +1, or 1 times -1. Again, in our image, move over 1 column, same row. 4, in our kernel, back up 1 column, times -1. Okay, that takes care of the first row. That's going to add to the next multiplication. Okay, the next multiplication is in our y subset, we are going to move to the next row, first column. In our kernel, we're going to move up 1 row, but remember we always move from right to left, so it'll be +7 times -1. Add to that, okay, once again, we are going to move over 1 column, same row in y, back up 1 column, same row in k. 8 times 8. Great, getting there. Tedious process. Now, over 1 column in y, 9, back 1 column in k, -1, same row. And we are going to add to that, and we have 1 more row to go. Okay, I'm running out of colors here. Let's see, this would be 7 times -1 plus 10 times -1 plus, and last but certainly not least, we'll have 1 times -1. Okay, great. Let's add these together. So we'll have -5 minus 1 minus 4. -5 minus 1 minus 4 is -6. This is going to be -10. So we have -10 plus -7 plus 64 is 57. Minus 9 is going to be 48. Plus -7 minus 10 is -17, -18. And so we have -28 plus 48 is going to give us a value of 20. So in our new matrix, remember we're not actually going to change that 8 to a 20 in this matrix, but that 8 will become a 20. Okay, so all we know right now is that that 8 in position 2, 2, this value right here now becomes a 20. And that is how we do the convolution for one value. Now keep in mind we have other values in this matrix. This has to be repeated times, and of course it can be very tedious to do by hand, which is why we would instruct a computer to do it. But by understanding how it takes place, it gives us an idea of what we would need to instruct the computer to do. Now, one curiosity we might have is, well, what do we do about the values along the edges, right? So I'm talking like the first column, the last column, the first row, and the last row, because if you think about it, you can't wrap a 3x3 box around it. And you might just say, okay, well, why don't we, if like we're working with 6 and we want to convolve on 6, why don't we just take the 3x3 immediately around it? And the reason is because that's often not quite how it works. The way we typically handle edges is because it is an edge and it's only 1 pixel. Now remember, we're talking megapixels in terms of real images and high resolution screens. So having 1 pixel or 1 column of pixels be unchanged will typically not be noticed. And if it is noticed, you could actually just delete those rows and those columns. So typically not a big deal. And pixels around the border of the image are left untouched. Since there are not pixels surrounding them in all directions, not typically a big deal, since the effects are often not noticed around the boundaries of an image. Sometimes you can notice them depending on what kind of alteration you do, and there are some ways to handle it, but it's not worth worrying about, since again, that's going to constitute 1 column out of hundreds or thousands of columns. Okay, next video we'll take a look at different types of kernels. So, okay, now we know how to do it, but how do we choose the values in that K matrix? Well, it depends on what we want to do. And we'll start with an intuitive example, and then we'll work our way to looking at a couple of variations of that. And finally, we'll wrap up with a video of, well, how do we actually do it? And how do we actually take a big image, plug it into a program, and have it do that matrix transformation for us?